All right, cool. So we are officially in Unit 4, which starts the second half of calculus. All right, so everything up to this point was learning derivatives, learning the application of derivatives, and all the different rules we have with that. That is the first big topic in calculus. The second big topic that we're going to spend just as much time on as we did derivatives is something called integrals. Okay, so you're going to become just as comfortable doing integration as you are doing derivatives. And it's a similar process to how we built up to derivatives. Okay, so with derivatives, we had to learn limits first and understand what limits were and how they were computed in order to learn what a derivative was. This is going to be the same exact thing with integration. In order to understand integration and exactly what an integral is doing and finding, we must first study and learn and refresh ourselves on sigma notation. Okay? The definition of a derivative uses limits in it, and the definition of an integral uses sigma in it. Okay? So I think it's, again, important that we understand how this works and how the operations work and all the shortcuts and all that stuff. Okay? Very similar to how limits work. This can be found in Appendix B in your book. So just a quick little reminder on a few things. We have probably seen this before at some point, this notation. Okay? That's sigma notation. It literally means the sum. Okay? So this little E symbol right here, the summation symbol, it tells us to add. That's what it means. It means to add up all of the values given a certain equation or a certain pattern. Okay? A few of the things is like this I right here. This represents the index, or another way of saying that is your variable. It's usually I for index, but honestly that variable changes all the time. Okay? Now, if you remember the m on the bottom, so I equals m, this is the integer value that tells us which term to start with. So like a lot of times that value is 1, meaning to start with the first term in a list. The top number here, n, this is going to be some integer value, some number that tells us to end. So for instance, it could be I equals 1 to 5, meaning find the sum of the first 5 numbers, like the first 5 terms from 1 to 5. Something like that. And AI, that just means our pattern, our equation. So like the values that we're adding up, starting off with a sub n. So that's the value of my first term, going to my next term, and then dot, 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 all the way to our last term. Okay, so we'll see examples of this moving on. But I'll show some examples on the next slide. But that's what this is saying, to add up the values in a given situation. So let's look at some examples real quick. It says, simplify the following. Notice that other letters can be used as the index of summation, so it's not always I. Okay, okay, number 1. It says, how we read this is it's saying, take the summation from I equals 1, so the first term, to the fourth term, given that the pattern is I squared. So what this is literally doing is it's taking the first term, the second term, the third term, all the way to the fourth term, and adding those together. So it was taking like 1 squared, and then it's taking 2 squared, so that's the second term, and then the third term squared, and then the fourth term squared. So this right here just tells us the pattern of what we're doing from the first term to the fourth term, right? And I mean, you can just do this in your head, in your calculator. You can write it out if you want. I don't really care, but that ends up being 30. That's all it's saying to do. This next one, okay, so the pattern is I. This means take the summation of I equals 3 to 10, so from the third term to the 10th term. Literally means just plug 3 through 10 in for I. So that's going to be 3 plus 4 plus 5 plus 6 and 7 and 8 and 9, all the way till we get to the 10th term. Okay. So it looks like we had 8 numbers there that we're adding together, and that sum ends up being 52. And again, this equation inside the summation, that's just an equation, and it's just wanting you to add up terms in that equation. So in this case right here, this is 2 to the j. Right? Now what this means is that we just plug 0 to 5 in for j and add those together. So that's 2 to the 0, 2 to the first, the second, third, the fourth, all the way up to the fifth. And I'm getting that to be 63. Now, it's really hard for me to teach how this is done in the calculator, but this can be done in the calculator. Like, there is a way to type literally this into the calculator. And I want to take a little side note real quick just to kind of help you. So if you have a graphing calculator, try to follow along with my steps here. So I'm just going to write this because the math is never going to be for you to just do this by hand. You'll have a calculator available. So you're going to press alpha, which is the green button, and you're going to hit the window button, which is at the top of the calculator. So alpha window. Okay. I believe that it is number 2. Okay. It looks like a summation symbol. You'll see that little summation symbol. So if you click that, you're going to have a blank thing to fill in. It's going to be like blank equals blank, blank on top, and then in parentheses, you're going to have another blank. Okay? You just fill in those values where you use x as your index. So you would say like x, for this example we just did, x equals 0. You would plug in 5 up the top, and right here you would do 2 to the x. And that'll give you the same answer. Okay? So that's how it's done in the calculator. So you can do number 4 in the calculator if you want. It just means to do 1 over 1 plus 1 over 2 plus 1 over 3 plus ... all the way to the end to where it's 1 over 7. Which in this case is 363 over 140. I'm not going to write out number 5, but you're plugging in 1, then you're plugging in 2, then you're plugging in 3. Try it in the calculator if you want, but I'm getting 13 over 52. Oh, and I love this last one. This is like kind of the same properties as a limit. The pattern or the equation is just 2, meaning the first term's value is 2, the second term's value is 2, the third term's value is 2, and the fourth term value is 2. So this is just equal to 8. And like I said, I'm sure you've done some stuff with summation in the past, but this is just a little refresher of what that is. Okay. And you're going to notice that a lot of the same properties that work with limits also work with summations. So here's a little theorem here. If c is just a constant that does not depend on I, so if it's just a number, like c could be 2, 3, 4, 5, then the following properties are true. If you have some pattern, c times some function. So for example, I'll give a little example right here. That could be the summation I equals 1 to 5 of 3x squared. You can rewrite that with the constant on the outside of the summation. So in this case, that would be like having 3 on the outside of the summation. And that summation is equivalent. For b and c, it's just like limits. You can split these apart. So you can have the summation I equals m to n of the first function, and then plus the summation I equals m to n of the second function. Same thing for subtraction. It's the same thing, but with a subtraction symbol. So I think those are pretty straightforward, and we're going to be using these properties to help us with the definition of an integral and solve some problems later on. Okay. All right, now you might have known all of the summation properties that we've talked about up to this point, but I'm pretty sure this next part is new. Okay? And these are very helpful for being able to do the definition of an integral later on down the road, being able to understand these identities. Okay? So again, we're going to let c be some constant, and n is a positive integer, and the following is true. Okay. Okay. First of all, the summation from I equals 1 to n of 1 is just going to be n. I mean, think about it. The pattern is 1, so that's 1 plus 1 plus 1 plus dot 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 all the way to my nth term, which is 1. So if I start out with my ith term and go all the way to my nth term, you're just adding n amount of 1s together. So this is just equal to n. So the summation of 1 from 1 to n is n. And because of the property of the constant, okay, because of the constant property we talked about in the previous slide, where the constant can come out and you're just left with 1 here, this is similar to saying c times the summation I equals 1 to n of 1, which we know is going to be c times n. So that's another property we need to know. Now, those are two I think are pretty straightforward, and I think you can kind of reason through. These last three, there are proofs online. Like the proof for C is pretty straightforward, but the proofs for D and E, I wouldn't stress about reasoning through. They're actually very long and extensive proofs. But the following is true. Okay? So the summation of just I, the summation of just I from 1 to n, is equivalent to n times n plus 1 over 2. Okay? That's just what it is. From the first term to the nth term, the summation of I is the same thing as doing n times n plus 1 over 2. You're going to have to memorize C, D, and E. The identity for I squared. So if I take the summation of I squared, that's the same thing as n times n plus 1, which is similar to above, but we're going to tack on a 2n plus 1, and instead of it being over 2, it's over 6. And lastly, the summation of I cubed from 1 to n is the same thing as C, but everything is squared. So n squared, n plus 1 squared, all over 4. Those are three identities we need to know. We're going to look at some examples of how this works in a sec. And these next three examples are pretty much doing the definition of an integral without understanding what we're doing yet. So much like how we were learning how to take the limits of functions, that's exactly what we're doing now. We're learning how to take the summation of functions, which is going to lead into the definition of an integral. So let's put all this into practice. Okay. It says to evaluate the following summation. So 1 to n. Whenever it says to evaluate, okay, it means to tell me what this is equal to. Tell me what this is equal to. And because it doesn't give me an explicit value of n that we're going to, like it's not saying I equals 1 to 5 or I equals 1 to 10 or something like that. Like I can't tell you an exact numerical value, but I can tell you an answer in terms of n, which is what it's asking me to do. Okay, so when I find an answer in terms of n, it'll be able to tell me the summation after any amount of terms involved with n. Okay. We're going to be using the properties that we've learned in the previous slide. In order to do that, first of all, though, we need to simplify down the expression. So we need to distribute and simplify the expression. So what we got is summation I equals 1 to n of 4i cubed minus 3i plus 2. And remember, I is my index here. It's my variable. We treat it just like we would x. Okay. Now, how we solve this is once we have it expanded out, the idea is to break it apart in its individual pieces. Okay? Because remember how we said that a summation can be broken up into individual components. So I think this next part's pretty straightforward. We're just going to do summation I equals 1 to n of 4i cubed. Subtract the summation of I equals 1 to n of 3i. And then plus the summation I equals 1 to n of 2. Okay. once we separate it apart, the idea is we're trying to get it down to our identities that we learned in the last slide. And in order to do that, I'm sure you see I cubed, all right, we got 2 right there. If you can take a constant out next, that would be a great next step. So take the 4 out, take the 3 out, take the 2 out. Let's see what we got. We have 4 summation I equals 1 to n of I cubed. And you can see my summation symbol start to really look crappy after a while. I apologize for that. Summation I equals 1 to n of I. And then over here, I'm going to have 2 on the outside. Summation I equals 1 to n of 1. Now, the cool thing is the idea is that we get it down to properties that we know, and it's going to get rid of the summations. We're going to be able to evaluate this summation because we know what these properties are equivalent to. Look at these. Look at these 3 summations that we just simplified it down to. We have identities for all 3 of those that we learned in the previous slide. We will be able to use those to evaluate this problem. So look, we learned from the previous slide that the summation of I cubed from 1 to n is nothing more than n squared. N squared times n plus 1 squared over 4. And then minus 3 times. We learned from the last slide that the summation of just I is going to be n times n plus 1 over 2. And we learned from the last slide that the summation of just 1 from 1 to n is just n. Okay. So what we just did is we evaluated this summation, got everything in terms of n, and we're set. Okay, now let's just simplify it a little bit. That's not too much simplification. 4's cancel. Maybe we can say 3 halves n. Let's just say n squared n plus 1 squared minus 3 halves n times n plus 1 plus 2n. Let's not get anything crazier than that. So what I did is I just showed that the summation from above, summation I equals 1 to n of that equation from above, so this equation all the way up here, I just showed that that is equivalent to that. Meaning, whatever n is, the summation is going to be equivalent to this, plugging in this. So we just evaluated that summation. Not bad. Okay. Let's try another example. This one's fun. So it's always the same steps. Don't let it look confusing. Okay? Don't let it look confusing. It's going to be, okay, the only thing that we've added onto this is that we're going to take the limit of whatever answer we get. Right? We're going to take the limit of what answer we get. So this is, again, building up to the idea of a definition of an integral. So just like the last example, let's start by finding the summation first. Let's start by evaluating that, and then we'll do the limit at the end. Okay. Same as before. Go ahead and distribute and simplify. Do everything you need to do. I'm going to do this as few steps as I can for you. So I'm going to have the limit. N approaches infinity. We'll evaluate that at the end. I got the summation I equals 1 to n, and I'm gonna distribute the 3n. So 3 over n times I squared over n squared is going to be 3i squared over n cubed plus 3 over n. Okay? So we're doing the same steps as before. We distribute everything out. Now let's split this up into multiple summations because we're trying to use those summation properties. Okay? I'll use brackets. We got the summation I equals 1 to n of 3i squared over n cubed plus the summation I equals 1 to n of 3 over n. Okay? And now the idea is to try to get it down to one of those properties that we talked about the last slide, was either to get it down to the summation of 1, I squared, or I cubed, and then we can plug something in that's not a summation. And remember what n was. N is just a number, so we can treat it like a constant. I is the only variable. So our constant property applies here. I can take this out as a constant, and I can take this out as a constant. So what I'm left with is the limit as n approaches infinity of the 3 over n cubed comes out. I'm left with the summation of I equals 1 to n of I squared plus 3 over n, the summation I equals 1 to n of just 1. Because that's a constant, I was able to bring it out. I'm just left with 1. Okay? So what I'm doing inside these brackets here is nothing more than the same example as above. Okay? The cool thing is that when we take the constants out, everything's been distributed, you're going to be left with something that's just I. Either it's I squared, I cubed, or just 1. And it's at that point we can use our properties to get rid of the summation and start evaluating it. So what we have is the limit as n approaches infinity of 3 over n cubed times, remember I squared was n, times n plus 1 times 2n plus 1 all over 6. Okay? Plus. We have 3 over n, and then the summation of just 1, we said that property was equal to n. Okay? And now that we've simplified it, now that we've figured it out, okay, all we have to do is take the limit of this. And I don't want this to scare you because this is just two rational equations being added together. And if I'm taking the limit to infinity of a rational equation, that's just n behavior. Okay? So first off, the n's cancel there, so we're good. Now what about the limit to infinity of this first part here? What's it going to be? Well, we got to compare the highest powers on top and on bottom. For instance, on top here, if I were to multiply all the leading terms together, if I were to FOIL this entire thing out, it would be 3 times n times n times 2n if I multiplied everything out. So the leading term on top, if I were to FOIL this, and you're welcome to go ahead and do it if you want, but I know the leading term, the highest power is going to be 6, because 3 times 2 is 6, n cubed, because there's 3 n's you're multiplying together. And on bottom, it's going to simplify down to 6n cubed. And if that's the case, if the leading term on top is n cubed and the leading term on bottom is n cubed, then by our n behavior rules, it's just going to be the leading coefficients, right? So if I take the limit as n approaches infinity, the limit of this first rational is just going to be 6. And over here, it's just 3. Okay? Oh, I'm sorry. 6 divided by 6. Not 6. 6 divided by 6 is the leading coefficient. I don't know why I just wrote 6. I'm sorry. 6 divided by 6 is 1. There we go. So the limit of this entire thing here is equal to 4. Okay, the limit of this entire thing here is equal to 4. Now that's the math behind it, and that's all I really wanted to learn today. Now you don't realize it, but we just did the definition of an integral. All right, I mean I've done this before with you in the past with definition of derivatives. You didn't realize we were doing it, but we did. Same thing here. We just did the definition of an integral without realizing it. We'll understand what that means later on down the road. But I just wanted to try an example. Okay. All right, now for sake of time, I got 6 minutes left. I might be able to do this one actually. Yeah, you know what? 6 minutes left. Let's go ahead and do it, so we can have the full notes completed, and you can have this resource to watch at your pleasure. Okay. So we got the limit of the summation. So let's start by doing that summation piece first. Okay, just leave the limit kind of tacked on here, so we don't forget about it. Start by distributing. Okay. Then we're going to take the constants out and turn it into separate sigma notations. It's very, very much the same steps. So I have the summation, I equals 1 to n. If I were to distribute this, it's going to be 1 times I cubed on top, so I cubed. And on bottom, it's going to be n times n cubed, so n to the 4. Plus 1 over n. Okay. Now, I'm going to go ahead and do this next step for sake of time, and I'm going to do the next two steps in one. So I'm going to go ahead and separate it as two separate sigmas, and I'm going to go ahead and take out the constants. The constants are 1 over n to the fourth and 1 over n. And I'm going to be left with I cubed and 1. So what that looks like is, okay, I'm going to take the 1 over n to the fourth out, and I got the summation of I equals 1 to n of I cubed. And separating it, I'm going to take the 1 over n out, and I'm left with the summation I equals 1 to n of just 1. So I did two steps there. I separated the summation, and I took out the constant. Okay. So now, in doing that, I've already gotten to the point where we have our identities for these summations. We know what the summation of I cubed and the summation of 1 are equivalent to. So I have the limit as n approaches infinity of 1 over n to the fourth multiplied by I cubed is nothing more than n squared times n plus 1 squared all over 4. And then plus, that's 1 over n, and we know that 1 is the same thing as n. And now we're going to take the limit of that. Okay? And it's pretty similar to the one we did before. The n's cancel. And really, I'm just worried about taking the limit of this rational piece here and just adding 1 to it. Okay. All right, so look at the leading coefficients on top and bottom because we're taking the limit to infinity. On top, it's 1 times n squared times n squared. So on the top, we're just going to have literally n to the fourth. If you multiply everything out, the leading coefficient is going to be n to the fourth. On bottom, the leading coefficient is 4n to the fourth. And because they're the same powers, if we take the leading coefficients, that's just going to be 1 over 4 plus 1, which equals 5/4. So if I were to take this summation from 1 to n and take the limit to infinity, meaning I'm taking the infinite sum of terms. That's what the limit means, right? A limit of n to infinity means that I'm taking the infinite amount of terms from 1 to n and adding them all together. And what is that limit, what is that sum going to be? In this case, 5/4. There's an interesting concept of what we're doing here, and we're going to talk about what this means, what this definition means later. And we're going to really define the definition of a derivative or of an integral later. But for now, we are just refreshing ourselves with how to do the math, and we're going to practice that a lot more. So we're able to get it done in 30 minutes, which is great. You also have some problems that you can do in the book to practice this. A38 means Appendix 38. It's in the back of your book, number 21 through 35, odd, and 43, 45, 46. Some good problems there to try those things out. Okay. All right. Well, good job, guys. Hope you'll have a great day, and we will talk to you soon. Bye-bye.